Hi everyone, welcome back. So, in this last section on gravitational fields, we're going to be looking at the orbital properties of satellites or moons or planets, or the orbital properties of something that's orbiting something else. Okay, so here is the relevant dot point from your study design. Model satellite motion, artificial moon or planet as uniform circular orbital motion, and you have a little equation there that you can use to talk about these things. All right, and that's the only dot point that covers anything to do with orbital motion. So it's kind of unclear as to the extent to which you need to know things. So we're going to just go through a bunch of stuff. Whether or not that's going to show up on an exam, who knows? Okay. Let's start off though by looking at satellite orbits and how we can think about them. So, just definitions of stuff, all right? So you've got something going around something else in space. We call that an orbit. Very rarely do things just fall straight down because there was some sideways motion there to begin with. Okay, it's a very rare circumstance that you'll get two things in space just falling straight towards each other. They'll generally have some other kind of motion with them because they're not the only two objects in space. So usually we say that a smaller object travels in some kind of path, which we're going to model as a circle, but we'll see that's not the case. So this smaller object travels around a more massive object. Okay, we call that an orbit, and the smaller one is called the satellite. Okay, satellite can be artificial satellite. It can be a moon of some kind, or in the case of planets and the sun, the planets would be the satellite in that case. Okay, but we don't refer to them as satellites. We call them planets because they're orbiting a star. Okay, with some other qualifications. So there you go. That's what we're talking about here. Okay, satellite motion, things in orbit. All right, so let's start by talking about these things called Kepler's Laws of Orbital Motion. Now, again, whether or not this thing's going to pop up on an exam, I have no idea. I haven't seen any questions about Kepler's laws on any previous exams. The only time I've ever seen them mentioned is in textbooks. But it's a good idea to cover it anyway because it gives you sort of a little bit of background knowledge, I guess, of what these orbital characteristics are. So Johannes Kepler, ages ago, he was the first one to really sort of study planetary motion and put all these laws into place based on his observations. Okay, and he's got 3 laws. And usually these 3 laws, in conjunction with Newton's universal law of gravitation, is enough to basically study the orbital characteristics of pretty much anything. So let's see what they are. So we've got first one. The planets move in elliptical orbits with the sun at one focus. Okay, bit cryptic. We'll see what that means in a second. Number 2, the line connecting a planet to the sun sweeps out equal areas in equal time intervals. Again, kind of cryptic, but we'll see a picture and it will become clear. And the third one, this one is the most relevant for you guys. It says, for every planet, the ratio of the cube of the average orbital radius r, okay, so the cube of that, to the square of the orbital period t is the same for all planets. Okay, so this ratio here, if you were to get the orbital radius of planet A and the orbital period of planet A, put them into this ratio, cubing and squaring where you need to, you do the same thing for planet B, it turns out that ratio is the same for both of those planets. Okay, so all of the planets orbiting the sun, which is what this law was originally sort of framed as being talking about, all of the planets have the same ratio of these particular orbital characteristics. And that's really interesting. And we'll see, we'll give a sort of a bit of a reason in one of the next videos as to why that's the case. All right, so let's unpack these. Okay, so the first law, all the planets orbit in an ellipse with the sun at one focus. So basically an ellipse is an elongated or stretched out circle. It looks like an oval, something like that. Okay, says every ellipse has 2 foci, which are the plural of focus. What is a focus? Well, there's these two special points inside the ellipse. There's one over here, roughly, and there's one over here. Okay, this is a mathematical object. All right, so don't stress too much if you don't really remember these terms. Just know that that shape is an ellipse, and there's these two spots inside it called foci. And when we're talking about satellite motion, you've got the satellite following this sort of elliptical path with the central massive object at one of the foci. So you might say that the sun is located here, all right, and the planet will go around like that. Okay, there's not really anything at the other focus. That's just sort of empty space. Just some more terminology down here, and you can read that yourself. So when you are furthest from the central body, that is called apsis. So that's this location here. And where you're closest, that's called periapsis. That's over here. Okay, if you're talking about planets orbiting the sun, we call them aphelion and perihelion. And if you're talking about the moon going around the Earth, then we call it apogee and perigee. That's it. Okay, so just some terminology there. That's what your ellipse looks like. That is a representation of how objects orbit other objects. Okay. Here's a picture, basically what I drew. There you go. Okay, so don't worry too much about it. You're just saying that's the shape of an orbit as one thing goes around something else. Cool. All right, second law. So the second law was, let's go back a little bit, read it. Okay, a line connecting a planet to the sun sweeps out equal areas in equal time intervals. So in this picture here, there's the sun. Here's the Earth going around in a very exaggerated orbit. Okay, the planets are actually very, very close to circular orbits. They look nothing like this. Okay, this is a very exaggerated picture. But what the second law is saying is basically this area here between, say, the 1st of December and the 1st of January is the same area as this part here, which is the same, which is from, say, the 1st of January to 1st of February. That is the same as this area here, which is the same as this area here, and this area here, and this area here. Okay, the point of this picture is trying to say that these intervals of time are roughly equal. Okay, don't worry too much about the fact that some months have 30 and some have 31 and February only has 28. What they're saying is when a planet, travels in its orbit in a period of 1 month, then if you were to connect that planet to the sun, it would sweep out this area. Okay? And if you do that every month, the area that gets swept out by the planet, that's the same for every period of those specific time intervals. So every month, the planet sweeps out a particular area, and all of these areas are exactly equal to each other. Okay? So what that would mean, if you're paying attention, is, well, look at the distance that it has to travel in order to make this area the same as something that's on the other side. So this area, both of them are the same, but because the distance to the planet and the sun is longer, it doesn't have to travel as much sideways to create this area than it does, say, over here. Okay, so things that are closer to their central masses during their orbit are orbiting more quickly, and when they're further away, they're orbiting more slowly. Okay, so that's something that you can take away from that. So that's Kepler's second law. Now the third law, this is the most relevant for you guys. So third law states that the cube of the average orbital radius divided by the square of the orbital period is the same for all the objects that are orbiting a central body of some kind. Okay, so in this case, Kepler's third law was talking about planets orbiting the sun. This ratio for all of those planets with those orbital characteristics is the same. Okay, and the original way that he sort of framed it was that if we represent the distance or the average distance between the Earth and the sun as 1 AU, which is an astronomical unit. Okay, so it's got a value of 1. And the period we represent in years, then this ratio is actually equal to the number 1. Okay, you could, of course, represent the distance in meters and the time in seconds, and you'd get a different number. It wouldn't be 1 anymore. But if we just define our distance to be in units of AU, and we define our period to be in units of days, or Earth days, Earth years, then this ratio will always end up being 1 for every planet that you talk about. Okay, so that's it. That's Kepler's laws. All right. Again, I don't really think that's going to pop up on an exam, but at least you know them now and you're aware of them. But like I said, this third law, that is the most relevant. Okay, and we'll see this again in the next video anyway, in a more generalized situation. All right, that's it. I'll see you guys in the next video.